Page 480 in your textbooks. We'll get to your homework momentarily. First, wanted to review some things we've been talking about over the last few days. We've been talking about these lists of numbers for the last week or so. Now, what do we call an ordered list of numbers, where there's a rule that determines what the next number in the list is? Brandon?
Sequence.
A sequence. And we talked about two major types of sequences, Kendall.
Arithmetic.
The one we've been working on more recently. Okay, Genesis? Geometric, arithmetic, geometric. Now we talked about recursive sequences also. Remember that have that a sub n minus 1 that refer back to a previous term. There's all kinds of different types of sequences you could have, I suppose. But the two major types are arithmetic, geometric. The key with arithmetic class is that you are going to add a certain constant called the common difference. But with the geometric sequence, Michael, we multiply by something called, well, we don't multiply by something called Maddie. Maddie, we multiply by something called, not the common difference, but, Abby? The common ratio. Okay, so keep them straight. Arithmetic add, geometric multiply. Arithmetic has a common difference, geometric has a common ratio. Now, if in an arithmetic sequence we have a negative common difference, that just means the numbers get smaller, right? Because we're subtracting in a sense. Practically, we're adding the inverse. With a geometric sequence, for the numbers to get smaller, we would have to multiply by what type of common ratio, Audrey? If we want the numbers to get smaller and smaller and smaller, 10 goes down to 5, goes down to 5 halves.
Convergent.
Okay, that's the type. That was actually going to be one of my follow-up questions to that. You stole my thunder. But what would the common ratio have to be to have a convergent sequence then? Class? A fraction, right? If you have a fraction for your common ratio, the numbers are going to get smaller and smaller and smaller. And we would call that type of sequence class A. Convergent sequence, as opposed to if you have a non-fraction or a bigger value, or technically even an improper fraction, where the numbers get bigger and bigger and bigger, then class you would have a divergent sequence. You can have a negative common ratio, but what happens? What's the effect of a negative common ratio on a geometric sequence? Genesis? Did you hear the question?
Mm-hmm.
Okay. If we have a negative common ratio, what effect does that have on the sequence? It's going to switch back and forth, so the word for that is, class? Alternating. It's going to be an alternating geometric sequence. Again, that's not going to happen with a negative common difference in an arithmetic sequence. It'll happen in a geometric sequence. What's that formula for the geometric sequence, Brandon? You're thinking series. We're not there yet. We're about to review that. Arithmetic or geometric sequence. Maddie, help. There we go. Okay, so a sub n equals a sub 1 times r to the n minus 1 is our formula for a geometric sequence. Now, from there, yesterday we began talking about the sum of the terms in a geometric sequence. And just the same thing as for arithmetic, the sum of the terms, class is referred to as a series. So a geometric series is simply the sum of the terms in the sequence. For our purposes, our geometric series will always start at 1. So we don't necessarily have a lower bound to upper bound to worry about, so we don't use the sigma notation for a geometric series. That's for an arithmetic series. For the geometric series, we use what letter instead, Kendall? Just a capital S. And so our formula for the sum of the first n terms is?
A sub 1 times 1 minus r n.
To the n. There we go. And so these are our geometric series, sequence geometric series formulas that we would have used at some point in our homework. Starting on page 480 there in the middle of the page, we had that middle review 10.5 section, numbers 9 through 12. You also have page 479, previous page 2 through 12 even. Let's take a look at that. There's 2 through 12 even. There's the 9 through 12. Excellent. 2 through 12 even, and there's the 9 through 12. Yeah, I kind of missed the idea of what we were doing there. Good, got it, and got it. All right, all done on the calculator. Good, excellent, and okay, there's the beginning part of those. Good. All right, page 480, middle of the page, number 9. Determine the next term of the geometric sequence. Well, what's the pattern? What's the common ratio that we are using here in number 9? Abby? 3/8. So we go to 8 down to 3, just make the ratio 3/8. If you're not sure about it, try multiplying 3/8 times the 3. Yep, that'll be 9/8. Try multiplying 9/8 times 3/8. There again, it gives you a 27/64. So the next term would be?
81/512.
81/512 is correct. Number 10. We'll go from a 2 to a 12 to a 72. What's the common ratio here, Genesis? Times 6. So the next term after 432? 2,592 is correct. So you figuring out what we were doing there?
I overthought it.
Overthought it? Yeah, a lot easier than you thought. Number 11, they wanted you to find the nth term in the sequence using the formula. And so we know that our basic formula is going to be this here. Now for number 11 specifically, since we're finding the 6th term, we'll, instead of saying a sub n class, we would say a sub 6 is equal to, instead of a sub 1, Michael, we would say
A sub 6?
well, a sub n is a sub 6. A sub 1 is, on number 11, 4, the first term. What's the common ratio?
7/4.
7/4, and the n minus 1 then means we're going to raise this 7/4 to the 5th power. So you plug all that into the calculator and it gives you a really weird fraction. If you have a fancy calculator, most of us, it'll give us a really weird decimal. What did you get for your answer, Michael?
147.85546.
That is not correct. Audrey?
65.6.
Yeah, 65.652, blah, 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 wherever you chose to round off. It didn't say where to round. Quizzes, tests, I'll tell you where to round, or I'll make sure they work out evenly, or work out to normal fractions. If you got a fraction, it'd be 16,807 over 256, 65.65. How many have the 65.65? Plug it into your calculator. If you didn't, double check it real quick. I would start with the 7/4 raised to the 5th, and then multiply that answer by 4. You should get 65.65 when you plug it back in. Anyone having issues with the calculator? Anyone have calculator issues, need help? Going once on help. Got it now?
I got 37 33/64.
This just now when you did it again?
No.
Yeah, rework it again. And then if you're not getting it, let me know. All right, Michael, you got it now? Then why weren't you raising your hand and letting me know, like I said?
I think I'm using the one on the right formula. Am I supposed to use the one on the left?
The one we were just doing on the left, that we wrote on the board just now as we were doing it, yes.
Okay.
It did, again, if it asks for the sum or the series, this is what this is for. The sum or the series. It didn't ask for the sum of the first 6 terms. It said, what is the 6th term? Do we see the difference? Not what's the sum of the first 6. That would be over here. That's a series. Just what's the 6th term? This is what we should be plugging into the calculator right now. Do we have that now? Okay. Anyone not getting this on the calculator now? All right, number 12. We are finding the 5th term. So again, since it's a geometric sequence, we need to find the 5th term using this formula. So class, we're going to do a sub 5 is equal to 10 times 1/7 to the 4th power. Now, you might be able to just do 7 to the 4th on your calculator. What is just 7 to the 4th, class? 2,401. So 1/7 to the 4th is going to be 1 2,700 first, right? But we're multiplying it by 10, which gives us 10 2,700 first. You could do it that way, or you could actually plug in the 1/7 to the 4th times 10. You get a really small decimal. Michael?
I'm getting 10 over 2,400.
Oh, 401, not 701, I'm sorry. I heard him and then my brain copied wrong number. So yes, some of you get in fraction, some of you should have decimal though.
I wrote it 0.004.
Yeah, 0.00416, blah, 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 something like that. Okay, questions on those? All right, so if nothing else, again, part of the purpose of homework is to help us make mistakes. It's okay to make mistakes as long as we learn from them. Do we see the difference between finding a term and finding the sum of terms? All right, excellent. We're flipping back then to page 479. Here we're finding the sum. Notice it says right there in the directions, find the sum of each indicated number of terms for the geometric sequence. So looking at the even numbered problems here, the page back where it belongs. Number 2, finding the sum of the first 4 terms, defined by a sub n equals 3/4 times 17 to the n minus 1. Well, this means that 3/4 is apparently the a sub 1, and apparently 17 is the r. So if I want the sum of the first 4 terms, class, then we would say I'm finding the series of the first 4 terms, s sub 4. In for the a sub 1 class, we'll plug in 3/4, because that's the first term, evidently, based on the algorithm they gave us. 1, and then we'll do 1 minus r, which is 17, and we're going to raise the 17 to the 4th power. So we're going to really big number right there, all over 1 minus the 17. That's how we should have plugged this in. You raise 17 to the 4th, subtract it from the 1, multiply by the 3/4, divide all of this by a negative 16, and it's actually not that super big. What is the sum of those 4 terms? Genesis? Yeah, plug it back into the calculator again. While you're doing that, Kendall, what did you get for number 2?
3,950.
That's what we should have been. How many had 3,915? All right, and then Genesis, plugging it back in. I want to confirm we know what we're doing. Take just a moment. Got it? Okay. Number 4, finding the sum, of the first 5 terms, defined by the algorithm a sub n equals 5 times 13 to the n minus 1. Again, if we want the sum of terms, we need to use this formula. Say it with me, class. S sub n equals a sub 1 times 1 minus r to the n all over 1 minus r. So for finding the the sum of the first 5 terms, then we'll have s sub 5 is equal to, what is the first term based on that algorithm that they gave us? Audrey? Yesterday did not help at all. 5. And 1 minus, what is the r based on the algorithm, Abby? 13, and we're raising it to the
5th. Or, yeah.
Yeah, the 5th power. All over 1 minus class 13. So again, you're going to raise 13 to the 5th, subtract from 1, multiply by 5, put all of that over a negative 12. What do we get for the sum of those first 5 terms? Maddie?
154,705.
Say it again?
154,705.
Good, 154,705 is correct. How many have that for number 4? Questions on number 4. Number 6, what did you get for your answer here? Starting with the first term of a half, common ratio 3, the sum of the first 10 terms, Michael?
I got 14,762.
Good, how many had 14,762? Question on that one. Number 8, they go ahead and start giving us the terms of the sequence. Well, obviously we can see a sub 1 class is 16, obviously it's the first term, right? But we have to find our own common ratio now. Not real hard. What's the common ratio here, Kendall? On number 8? The R value? 4. Hopefully you had an R value of 4 as you plug it in. So we end up with a S sub, let's see, we're finding the sum of the first 5 terms. So again, S sub 5 equals 16 times 1 minus 4 raised to the 5th power, all over 1 minus 4. What was the sum of those first 5 terms, Kendall?
5,456.
Good. How many had 5,456? Question. All right, number 10. Again, first 5 terms. 13, 52, 208. Obviously, first term class, a sub I, a sub 1, 13. What's the common ratio, R? 4 again. And we plug that in. What do we get for the sum, Abby?
4,433.
4,433. And then the next one's fun because we got the first 10 terms. Here, the common ratio class, 3, obviously, first term, 3. What do we get for the sum of the first 10 terms, Audrey?
88,572.
88,572. How many had that for number 12? Okay, questions on that? Any questions on the finite geometric series? Finite meaning a predefined set number of terms. Questions? All right, well, I alluded to this yesterday, the infinite geometric series, next section in your notes, the infinite geometric series. And I alluded to this yesterday, that we were going to be talking about it today, and kind of already referenced some things here, but for the infinite geometric series, this would be if we find the sum of literally every single term without ending in a particular series. And hopefully, if your brain's engaged, just as you think about the sum of all the terms in a never-ending series, you realize something. If this geometric series is a divergent series, meaning the numbers go closer and closer and closer to infinity, or closer and closer and closer to negative infinity, then obviously when you add all of those terms, including infinity, together, you're going to get infinity. Or you have all these terms, including negative infinity, together, you're going to get negative infinity, right? So if it's divergent, because the r sub n is almost or practically equal to either infinity or negative infinity, then therefore the sum of all of those infinite terms going to infinity is going to be infinity, or we would simply say no finite value. Or no finite sum might even be the better word, actually. I think is what how the book phrases it. The sum is no finite value. The answer would be no finite sum for a series of all the terms in an infinite series. That's if the sequence is divergent. It goes to infinity or negative infinity. But if the series is convergent, remember, that's where the numbers get smaller and smaller and smaller and smaller, closer and closer, class, to where you basically are adding nothing. Right? I mean, picture a pizza, and we cut it in half, right? And we have this half. And then we cut the other half into a fourth, and we add that fourth on. And then we cut the remaining fourth in half, and we add that eighth back on. And we cut that eighth in half, and we just keep cutting in smaller and smaller slices. Well, eventually you're going to get to the point where you're virtually adding nothing back, but the whole pizza would add back to one of itself, correct? Look back at page 477. There's a bit of an illustration here, kind of a picture here. They start with a full value and go with a common ratio of a half, but they say, well, let's suppose you started with 1, then you added half more, and then another quarter more, and then an eighth more, and then a 16th, and then a 32nd. Eventually you're going to be adding such tiny little pieces, but it's all just kind of going to add up to the 2. So because the r sub n, by the time you get to the last, which there isn't a last, but theoretically last-ish term in the series, you're going to be virtually adding nothing. So if you think about this for just a moment, this r sub n becomes basically 0, doesn't it? So if that's the case, then you have 1 minus nothing, class, which is 1. And a sub 1 times 1 is a sub 1, right? Anything times 1 is itself. So basically, we end up with this, that S sub n for an infinite convergent geometric series is going to equal just a sub 1 over 1 minus r, because this whole little parenthesis nonsense just disappears. Go and write this in your notes, and then also go back to your formula page and write that down as formula number 11, I believe, the infinite convergent series. The infinite convergent series. Infinite convergent series. The previous formula should say finite geometric series. Is that correct? Formula 10, finite geometric series. This is infinite convergent series. It's geometric also, but it's a lot of words to write. Infinite, it never ends. Convergent, specifically, geometric series. Do you realize, though, it's not a new formula? We're writing it as if it is. It's really the old formula with the parentheses gone, because it just gets smaller to nothingness anyway. Does that make sense? Questions? All right, look at page 478 now. Page 478. And look at the example 10.5e. Page 478, example 10.5e. And notice it says here, find the sum of the infinite geometric series defined by this sequence. So again, we're not finding the sum of the first 12 terms. We're finding the sum of every single term that could ever be put into this sequence. Does that make sense? 3, 1, a third, a ninth, a 27th. What would the next term be, by the way, just out of curiosity? 181st. That's not much of nothing, probably. Unless you're talking about like an 81st of, Elon Musk's money. Then an 81st is a whole lot of money. All right, the next fraction would be 1/243rd, 1/729. Right, the values just keep getting smaller and smaller and smaller. Clearly, this is a convergent sequence, correct? If it's convergent, you can find the sum. If it's divergent, there is no finite sum, right? But this time there will be. So to find the series or the sum, we're going to take the first term class, 3, over 1 minus the common ratio. What's the common ratio here? A third. So 1 minus a third. And so what is 1 minus a third, by the way? 2/3. So we're going to take 3 divided by 2/3. You can do that on the calculator using your fraction feature. 3, use the division key, and then use the fraction key to enter 2/3. 3 divided by 2/3. And we end up coming up with, class? Well, 9/2 or 4.5, right? Nothing wrong with 9/2. You could have 4.5, you could have 4 1/2. Any of those answers would suffice. So you kept adding and adding and adding. Now, frankly, if you just took the first few that are actually written, that's almost 4.5 already, isn't it? All right, literally on your calculator, do that. 3 plus 1 plus a third plus a ninth plus a 27th. 3 plus, just the 5 numbers that they have pictured. 3 plus 1 plus a third plus a ninth plus 1/27th. And what is your calculator giving you?
4, 13, 26.
4 and 13/27. You realize 4 and 13/26 would be 4.5. This is almost 4.5 already, just from the first 5 values. Because each thing that you add adds virtually nothing, just that tiny bit closer and closer and closer to 4.5. Questions on that problem? Look at the next example, 10.5f. They give us another geometric series. They want the sum of all the terms. Well, again, if they only wanted some of the terms, we could figure out how many, add them all together. But they don't want that. They want every single term. Look at the sequence, 5, 10, 20, 40, 80. What are we doing each time, class?
Bigger.
Well, bigger, yes, more specifically, we're doubling, right? We're doubling, multiplying by 2. Well, eventually at the end of the line, what's the last term going to be? Infinity. So if you add infinity plus all the other big numbers before it, what do you get? So notice their answer was simply no finite sum. It's a divergent series or sequence, so the series of a divergent sequence is infinite. No finite sum. Make sense? Look at the next example. 4, 3, 9/4, 27/16, 81/64. Are the numbers getting bigger or smaller? Smaller. Not very quickly, but they are getting smaller, aren't they? All right, what's the common ratio here? 3/4. So if I want an infinite series, I'm going to go with this formula. We're going to start with the a sub 1 class, 4. And we're going to do 1 minus the common ratio, which is simply 3/4. And of course, what is 1 minus 3/4? 1/4. So do 4 divided by a 4th. You might be able to do that in your head. 16, right? Division by a fraction is multiplied by the reciprocal. So if you had all the terms in that particular sequence together, you would get 16. Questions on how to use this formula? You can only use it so long as it's convergent, so long as values are getting smaller. If it's divergent, you just say no finite sum and you're done with the problem. Page 480. Turn the page and look at the top of the page. Page 480. Look at the top of the page, and number 17 at the top. It starts off with a 2, a 1, a 1/2, a 1/4. We realized we could keep going infinitely. And if we did go infinitely, what would be the sum of all the terms? Not the sum of the first 7 or the sum of the first 12, but literally the sum of all of them, which is what n could mean, just all of them collectively. Well, for this we need the formula, class. A sub 1 over 1 minus r. Again, S sub n equals a sub 1 over 1 minus r. Just taking this little piece out from the finite series. What's the a sub 1, class? 2. Over 1 minus, what's the common ratio, Genesis? A half. What's 2 minus a half, class? Or what's 1 minus a half, class? A half. You could do that on the calculator if you needed to. What's 2 divided by a half? 4. And again, you could do that on the calculator if you needed to. Now it says you have to do these in your head. You could certainly use calculator. Questions on number 17. Drop down to number 20. Number 20. Look at the values you got. You got 4. You got 44. You got 484. That just keeps on going and going and going. Are the numbers getting bigger or smaller? Bigger. So if you add them all together, what you going to get? Infinite. So we'll simply say no finite sum. It's just too big. Questions on that? Seem pretty easy. Now we're working it. Okay. 21. Go from 6 to 4 to 8 thirds to 16 ninths. How am I going to set this up, Brandon?
S of n equals 6 minus
6 over.
Oh, 6 over 1 minus 2 thirds.
Good. 4/6 or 2 thirds would work. Just taking the ratio of 4 to 6. And of course, 1 minus 2 thirds, class? 1 third. And 6 divided by a third?
18.
18. If we added all those little bitty fractions together at the end, it would all add up to exactly 18. Number 24. We got a 4, and a 9, and an 81 fourths, and whatever else comes next, 729 sixteenths. And what's the common ratio? Class? 9 fourths. Is that bigger than 1 or less than 1? Bigger than 1. So is this convergent or divergent? Divergent. These numbers are getting bigger, aren't they? 4, 9. This, you say, well, that's a fraction, right? But what's it equal to? 20 and a fourth? That's bigger than 9. 729 sixteenths. What's that equal to? Like, I don't know, 40 something, 50 something, 40 something ish, right? So that's going to be a big number. They keep getting bigger and bigger and bigger. So no finite sum. Good. No finite sum. Questions on those? All right, do 18, 19, 22, and 23. 18, 19, 22, and 23. Let's take a look at these together. Number 18, what did you get for the sum of all the terms in that sequence? Maddie? I'm sorry?
81/8.
Yes, 81/8 would work as an answer. It's not what I've got in my book. Or 10 1/8 would also work, or 10.125, any of those. 81/8, I like it. How many had one of those three answers? Either 81/8, 10.125, or 10 1/8. Excellent. Number 19, what did you get for your answer, Michael?
No finite solution or sum.
Right, no finite sum. They are still getting slightly bigger every time. Not much, but slightly. And since you have to add all these terms together, it's going to be infinity. Number 22, what did you get for your answer, Brandon?
No finite sum.
These getting much bigger more rapidly, no finite sum. How about number 23, Genesis?
26.
20 1/6, or you might have had 121/6, or you might have had 20.16666, and so forth, right? Just keeps on going forever. How many had one of those answers for 23? Any questions on these four? All right, you're going to practice more with this for homework tonight, but I do want to, as we look ahead toward a test coming up Wednesday, review over the other sequences in series, because the challenging thing about this section is it changes gears. It doesn't so much build, it changes. And so I want to make sure we remember what we're doing here. Drop down to the bottom, page 480, and then onto the top of the next page. Do 1 through 7, the odd. So page 480 at the bottom to page 481 at the top. Do 1 through 7, the odd, and let's go back and review some of the first things we talked about in this section, just to make sure we don't get things mixed up. Abby's finished. Michael's finished. Abby's changing something. Now Abby's finished. Brandon's finished. It's true. It's because she has the water bottle on her desk. That's what it is.
Exactly.
Just doing 1, 3, 5, 7. right, let's go and take a look at these together. Number one, they give us an algorithm, a sub n equals 12n negative 20. And this is, as it turns out, an arithmetic sequence. It's not written in that form as far as the algorithm goes, but what are those first 6 terms? Kendall?
-8, 4, 16, 20, 40, 52.
How many had negative 8, 4, 16, 28, 40, and 52? Okay, questions on that? Anyone need to see that worked out? See, I did not get that. I'm confused. Any questions? All right, number 3. They give us a recursive sequence. We know from the a sub n minus 1, that and in the directions it said there was a recursive sequence. They also gave us a sub 1 as 2. What did you get for the first 5 terms here? Genesis? Got stuck on that one. Okay, we'll work it in just a moment. Let's come to Abby. What did you get for your answer?
2, 6, 18, 54, 162.
That is not correct because you gambled. You treated it like a geometric sequence instead of an arithmetic, or instead of a recursive sequence. Audrey? You did the same thing. The problem was you looked at the first 2 numbers and gambled on the connection, and that wasn't it. You had to go with at least the first 3 to see the connection. Not you. Well, sure, you.
2, 6, 12, 20, 30.
There we go, 2, 6, 12, 20, 30. So Genesis, you were not the only one who was stuck here. Let's take a look. We've got a sub n is equal to a sub n minus 1 plus 2n, and we're finding the first, second, third, fourth, fifth terms. Obviously the first term, a sub 1, they gave to us is 2. Well, when we come to a sub 2, class, we're going to start by looking at the, what does this mean? Previous term, which is a 2, but the term number is a 2. So we're going to do 2 plus 2 times 2, and that's where we get the 6. But the problem is that doesn't mean we're necessarily multiplying by 3. Come to a sub 3. Well, again, the term number is a 3. The previous term now is a 6. 6 plus 6 gives us 12. So is it a tripling effect? No, and that's where like, okay, well, I guess I don't have a shortcut. We're going to have to do this a slow, painful way. Now this changes out to a 4. This changes out now to a 12. Previous term 12, term number 4. That's where we got the 8 plus 12 is 20. So, at your seats, unless you already had it correct like Maddie, what is that 5th term? 30, right? Because you get the 2 times 5 from the 5th term plus the 20, which is the previous, ends us with that 30. And there's the first 5 terms. Does that make sense? Any questions on that one? All right, let's take a look at number 5, determine the next term of the arithmetic sequence. They specifically told us it was arithmetic. That helps. Back to Genesis. 31. The common difference there is simply a 7. For number 7, how many had 31 for number 5? Anybody to see that one work? All right, number 7, they wanted the 10th term of the arithmetic sequence, given a first term of 3 and a common difference of -4. Abby, we come back to you. What's the formula for an arithmetic sequence?
A sub 1 plus the quantity n minus 1 times d.
There we go. A sub n is equal to a sub 1 plus the quantity n minus 1 times d, the common difference. So since they want specifically the number 7, the 10th term, we'll be finding a sub 10, where we know a sub 1, they tell us is 3. The n minus 1 becomes what number?
9.
9, 1 less than the term we're finding. The common difference they specifically said was -4. What is the 10th term?
-33.
-33. How many had that for number 7? Okay, questions at all on that? A little while since we've done some of those, at least a few days. Questions? Anyone perfect on all 4? All of them right? Okay, a couple of you, a few of you, good. Anyone just missed that recursive one? All right, that was the only one you missed. Questions at all on those? All right, do 9 to 15 the odd. Do 9 through 15 the odd. Practicing now with the series. 9 through 15 odd. If you need to go back to your formula page, by all means, do so. That's why you have a formula page. Though you won't be able to use it on the test. So make sure you have it memorized in time for the test. Or, you know, give large sums of money as donations to your math teacher, and maybe the formulas will appear like on a matching section or something on the test. It could be arranged. It could be arranged. The right sum. See how I used the math word there? Sum.
How would it be the cube root of 3 cents?
You don't have the cube root of 3 cents.
But I could cut up the thing.
Abby's done. Audrey's done. Just another minute or so to be finishing. So what?
He was happy that he beat me, but then I told him that I did all, and it ruined his happiness.
You ruined your happiness. So in other words, on Monday, he's going to be looking at you like, ha, I'm done already.
Mm-hmm. What are we doing Monday?
The evenings?
Oh. Haha.
Just do a report on Monday.
That's what I don't do all.
Can I bring other school books on Monday?
You just gonna sit there and report? Did you work at it?
How nice.
Hide your eyes. There you go. All right, pencils down. Even if you're not done with all of these, let's take a look. This first one, just on the surface, it looks nasty. And some of you might be thinking, well, I could split this into 1/3 series of I plus 2 times the series of I from 1 to 3. You could do that, but it's from 1 to 3. Like, that's not much. I think their intent, honestly, was that the easiest approach is just plug in the numbers. Plug in a 1 class, and if you plug in a 1, you get 1/3 plus 2. What's 1/3 plus 2? 2 1/3. Now plug in 2. That gives us 2/3 plus 4. What's 2/3 plus 4? 4 and 2/3. And we're already to the upper bound, we plug in the 3. Well, plug in the 3, I get 1 plus 6 gives 7, and I get 14. And I think that was actually easier than taking the time to split it. You could, and it should still give you a 14, but I think it's probably easier just to plug in the numbers. If it's going to be that small, just plug it in. This next one, I'm not 1 plus 2 plus 3 plus 4, all the way up to 31. I'm going to use the formula. What's the formula for a series of consecutive integers, class? N. Good. N times n plus 1 all over 2. So the n is 31 times 32 all over, or in other words, 31 times 16. And we end up getting what for our answer, class? 496. And we have that for number 11. Number 13, it's a partial consecutive series, right? It's still a series of I, but it goes from 11 to 30. What we said the key is to, first of all, class, find the series of I from 1 to 30, and then subtract away the series of I from 1 to 10. Subtract away everything below what I need. So from 1 to 30, we use that same formula, n times n plus 1 over 2. N 30 times n plus 1 all over 2. Or in other words, 15 times 31, which is 465. All right, and then here, n 10. Louder, please, so I can hear you. Everyone answering, not relying on Brandon. N plus 1, class. 11 all over 2, or basically 5 times 11, or 55. We subtracted away class, we get 410. I like to hear all the voices. And I know everyone's going to pass the quiz on Monday. Everyone's going to pass the test. It's going to be great. I like to hear everyone answering. How many have 410? Questions?
I just mix the numbers when I write them.
Okay. All right, and then the last one here. This one we do, since it's 1 to 13, I don't want to plug in 1 all the way to 13. So here I will split this up. And what does this end up being rewritten as? Genesis? Yep.
2 times the
Series.
series of 30 minus.
Did you say I? 2 times the series of I?
2 times series of I minus the series of 4.
There we go. 2 times the series of I minus the series of 4. And in each case going from 1 to 13. Again, for this, since once again for the third time in a row it's consecutive integers, class, n times n minus, or n plus 1 all over, but I'm going to end up multiplying by this other 2, right? So this 2 down here and this 2 out here could just cancel, so it could just be 13 times 14, class.
3,045.
13 times 14? 182? All right, and then here, since it's a constant series, what's the formula for a constant series, class? Just C times n, right? So 4 times 13, which is 52. And we'll subtract it from 182 to get 130. And how many have that for number 15? Questions on these series. It hasn't been that long, just a few days, but it's amazing when you don't use something, right? When something, because most of math, let's be honest, most of math this year builds, right? We learn something, we go to the next thing, but we're still using it. Go to the next thing, but we're still using it. This section doesn't build, which makes it easy to forget stuff if you don't refresh your memory. So your homework for the weekend, first of all, study. Study. Don't wait till Tuesday night. We got tests coming up Wednesday. Don't wait till Tuesday night to study. Start studying this weekend. Tests coming up in lesson 156. By the way, here's some sections to study. 6.1 to 6.3 are matrices. 6.1 to 6.3 are your sections that we covered on matrices. Now the chapter's bigger than that, but we don't cover the whole chapter. We only did section 6.1 to 6.3. And then in this chapter, we did 10.1, 10.2, skipped 10.3, and 10.4, 10.5. So 10.3, an optional section we opted not to cover, since we got a lot we got to cram into this quarter. So 6.1 to 6.3, 10.1 to 10.2, 10.4 to 10.5. Study begin this weekend. Also on page 493, to specifically help you practice the new material today with infinite convergent geometric series, page 493, numbers 15 to 24. Page 493, numbers 15 to 24. Take a look at that. On Monday, we'll be reviewing some on Monday, reviewing certainly on Tuesday, special emphasis on matrices on Tuesday, and then Wednesday will be your test. Have a wonderful rest of your day, a wonderful weekend, and you are dismissed.